Hi, welcome to Sunil Maths tutorial, functional analysis class number 36. In this video, we learn a theorem. Let us see the statement of that theorem. Capital M be a closed linear subspace of a Hilbert space capital H. X be a vector not in capital M and D be the distance from the element X to capital M. Then there exists a unique vector y0 in capital M satisfying this condition. Norm x minus y0 is equals to d. So first we write the introduction part of this theorem. Let us see. H be a Hilbert space. Capital H be a Hilbert space. And capital M be a closed linear subspace of capital M, capital H. M is a closed subspace of the Hilbert space capital H, and X is a vector. X is a vector not in capital M, does not lies in capital M. X does not belongs to capital M. So define D is equals to infimum of norm x minus z such that z belongs to capital M. It means d is the distance. From x to m. And we have to show that. We have to prove that there exists a vector y0 in capital M. There exists a vector y0 in capital M satisfying the condition norm x minus y0 is equals to d. And also you have to show that this y0 is a unique vector. So right. To prove this, we use the definition of D. Here what is D? We define D as infimum of norm x minus z such that z belongs to capital M. So D is an infimum. So by definition of D, there exists a sequence yn in capital M. Such that norm x minus yn converges to D as n tends to infinity. This is from the definition of D. So in another words, it can be written as limit n tends to infinity norm x minus yn is equals to D. Now take any two elements. Yn and ym from the sequence yn. Then obviously norm x minus ym is equals to D, as well as norm x minus yn is also equivalent to D. Right. Again, since capital M is closed, you assume that here it is even proper. Here it is a convex property also. Here it is M is closed as well as convex. Just it is an assumption. If M is convex also, then you can write like this. M is convex and yn comma ym belongs to capital M implies as yn plus ym by 2 also belongs to capital M. Okay. By applying the definition of D now, norm x minus yn plus ym by 2 is equals to D. Apply the parallelogram law. By parallelogram law, apply the parallelogram law for the vectors. x minus ym and x minus yn. Now let us apply this parallelogram law for the two elements x minus ym and x minus yn. So you can write like this: norm x minus ym plus x minus yn whole square, norm x minus ym plus norm x minus yn whole square plus norm x minus ym minus norm x minus ym minus x minus yn whole square is equals to 2 into norm x minus ym whole square plus 2 into norm x minus yn whole square. Am I right? It's absolutely right. This condition is absolutely right. You can write, which implies as norm x minus ym minus x minus yn whole square is equals to 2 into norm x minus ym whole square plus 2 into norm x minus yn whole square minus of norm x minus ym plus x minus yn whole square. This is nothing but 2 into d square plus 2 into d square minus 4d square, which is obviously 0. So this condition implies as in the left side we have this term norm x minus ym minus x minus yn whole square is equals to 0 as m comma n tends to infinity, which implies norm minus ym plus yn whole square is equals to 0, because x minus x get cancelled here. So which implies as norm yn minus ym is equals to 0, which implies as norm yn minus ym tends to 0 as m comma n tends to infinity. This condition shows us the sequence yn is a Cauchy sequence, in capital M. In capital M. Yn is a Cauchy sequence in capital M. Right. Already we know that H is a Hilbert space. Every Hilbert space is complex Banach space. Every Banach space is complete. Therefore H is complete. H is complete and M is closed in H, closed subspace of H. It means M is complete. And the sequence Yn is Cauchy sequence. In capital M. We know that every Cauchy sequence in a complete space is convergent. Therefore, the sequence Yn is convergent. Take the sequence Yn converges to Y0 in capital M. That is, limit n tends to infinity, Yn is equals to Y0. Now calculate norm x minus Y0. Norm x minus Y0 is equals to norm x minus limit n tends to infinity Yn, which is equals to limit n tends to infinity norm x minus Yn, which is equals to limit n tends to infinity d. D is a constant, limit cannot be applied, d. Therefore we prove that norm x minus Y0 is equals to d. That is, there exists a vector Y0 in capital M satisfying the condition norm x minus Y0 is equals to d. This is actually we want to prove that. But actually we want to prove that. Hence, it is remaining to prove that this Y0 is unique. We have to prove that now. We prove that this y naught is unique. Unique means there is only one vector satisfying this condition. Assume that if possible, if possible, suppose that, if possible, suppose that there exists another vector, there exists another vector y1 in capital M such that norm x minus y1 is equals to d. Norm x minus y1 is equals to d. It means now we have two vectors satisfying the same condition. One is y0, the second one is y1. Both belongs to capital M, which implies y0 plus y1 by 2 also belongs to capital M by the definition of convexity. Now apply the parallelogram law again. By parallelogram law, norm x minus y0 plus x minus y1 whole square plus norm x minus y0 minus x minus y1 whole square is equals to 2 norm x minus y0 whole square plus 2 norm x minus y1 whole square. So this is very obviously, this condition can be written as norm x minus y0 plus x minus y1 whole square is equals to 2 norm x minus y0 whole square plus 2 norm x minus y1 whole square minus norm x minus y0 plus x minus y1 whole square, which is equals to 2d square plus 2d square minus 4d square. Obviously it is 0. So what we show that norm x minus y0, therefore we conclude that norm x minus y0 plus x minus y1 whole square is equals to 0. This condition implies as norm y minus y0, norm y1 minus y0 whole square is equals to 0. This is nothing but norm y1 minus y0 is equals to 0, which implies y1 is equals to y0. Therefore, y0 is a unique vector. Y0 is a unique vector in capital M satisfying the condition norm x minus y0, norm x minus y0 is equals to d. Norm x minus y0 is equals to d. That's it. This is the required condition, hence proved. In the next video, we learn one more theorem. M is a, we learn one more theorem. Keep learning. Wish you all the best.